Hello everybody, and welcome to Day 9 of Climate Change. Last time we were together, we took a look at climate models, how they work, what they can tell us, and the uncertainties within them. In class, a lot of you wanted to talk about the role that feedback loops play into the outcomes of climate models. Well, fortunately, that's the topic for today. So come on along, let's learn. Our quote for today comes from the President of France, Emmanuel Macron, who says, "Never has science around the world been so abundant to meet the challenges that we have." By the end of today, you will be able to explain what positive and negative feedback loops are and how they impact Earth's climate. I'd like to remind you all that for our next class, we will be having our second journal club meeting, where we will read Keeling from 1976, and we will learn about the discovery of the increase in carbon dioxide in the atmosphere and its cyclical nature. When we come together in class, we are going to have a discussion in breakout groups about what positive feedback is. I'll ask you to give an example of a positive feedback loop that impacts Earth's climate, what the implications are of that, and how this adds uncertainty to climate models. I will also ask your group, what is negative feedback? I'll ask you to give an example of negative feedback and how that impacts Earth's climate. What are the implications of that, and how that impacts the uncertainty of models. I think a lot of you have probably heard about feedback in your biology classes. And this feedback is the same way. So our negative feedback is something that causes a resistance to overall change. And in a climate system, these are things that we can think of as being good. These are things that cause a stable climate to occur. A positive feedback is something that enhances or accelerates a change. From a climate perspective, we can think of these as being bad, or things that want to throw the stability of the climate system out of whack. And so essentially, you have an input, there's a process, and the output of that process impacts the process itself. And it can either impact that process in a way that reduces it or increases it. Tipping points are something that we hear about with climate change a lot. Those, is it too far, or have we gone too far, or can we change it, are points that occur when climate rapidly shifts from one stable state to another. And these can occur if a negative feedback loop system gets overwhelmed and no longer is able to function properly, or if a positive feedback loop kicks in and works to rapidly move Earth to another stable state. What are some negative feedback loops in the climate system? The first one is clouds. So if we have low-level clouds, these reflect light back into space, and they prevent visible light from reaching Earth's surface. And so we look in our example here, we have a lot of clouds that prevents light from coming to the surface. Clouds have a high albedo, light reflects back up, that light doesn't warm, and the higher the temperatures are, the more evaporation there is, therefore there's more cloud cover, therefore less light reaches the surface. Now, another negative feedback loop in the climate system is Le Chatelier's principle. And you should remember from your chemistry classes about equilibrium. And this principle is how the oceans are able to absorb carbon dioxide from the atmosphere and causes a buffering effect on the concentration of CO2 present in the air. And so what happens is the carbon dioxide in the air dissolves into the ocean. And if that was it, then the amount of carbon dioxide that could be stored in the ocean would be limited by this one equilibrium expression. However, carbon dioxide, once dissolved into the water, actually reacts with it, forming carbonic acid, and then that carbonic acid can go forward and keep reacting with other substances in the water as well. And we're going to take a whole day and talk about this in our second unit. So what happens? Well, the ocean can end up keep sucking in more and more carbon dioxide, because what it goes to, dissolved CO2, doesn't hang around in that form. It moves on and opens up more space for it to come. This is a negative feedback loop. Now, I just gave you 2 examples of negative feedback in the climate system, but you're going to see considerably more examples of positive feedback coming up for us right here. And the first one is clouds. And you'll think it's weird because we just talked about clouds, but while we just talked about clouds, those were low-level clouds. And if we talk about high-level clouds or mid-level clouds, these occur more frequently under warmer conditions because water vapor can rise farther into the atmosphere before it cools and condenses, and mid-level and high-level clouds trap more heat than they reflect. So what's the net effect of clouds on the climate system, considering that they both have a negative and positive feedback contribution? Well, that's a source of uncertainty. Another positive feedback that we've already talked about is ice albedo. Ice is more reflective than seawater. As Earth warms, the ice melts, exposing more seawater. The seawater absorbs more light than the ice, which causes the Earth to warm up more and causes the ice to further melt. We've got water vapor. As Earth warms, the saturation point of the vapor pressure increases because warm air can hold more water vapor than cold air. And that's why it's drier in the winter than the summer. You get nosebleeds, those happen more in the winter. You get your skin cracking in the winter because that cold air can't hold as much water vapor. Well, as we warm it up, we can hold more water vapor. And when the Earth is warmer, we are having higher evaporation rates. And water vapor is a greenhouse gas. So the warmer it is, the more water vapor is present in the air. The warmer it gets, the more water vapor, the warmer it gets. Next, we've got rainforest die-off. And so here's an example from the Amazon rainforest. And we'll start with temperatures rising. So if we raise temperatures, drought and wildfire increases in the Amazon. That leads to more trees dying and decomposing or burning, which releases more CO2. The rainforest has fewer trees, which means less water is pumped into the atmosphere from evapotranspiration. That causes rainfall to decrease. And that decreasing rainfall causes more drought and wildfires, which causes more trees to die. And so that's how we end up seeing a desertification in areas of the rainforest. And once that gets going, it tends to accelerate. Let's look at a couple more. We've got from the carbon cycle, a series of them. One of those is Arctic methane release. And so in the permafrost up in the Arctic, there's a whole bunch of carbon stored as methane gas. And that doesn't escape because it's trapped inside of ice. However, when you melt the ice, that releases that methane. And methane is a very potent greenhouse gas which warms the Earth and causes the permafrost to melt further, therefore releasing more methane. Methane can be released from other sources as well. We tend to hear the most about the Arctic methane, probably because it's the easiest one to understand for somebody who's a non-scientist. But one of the other sources of methane is methane being stored in hydrates. And so ice can form with methane in its crystal structure. So not just trapped in bubbles, but actually incorporated into the crystal structure of the ice. So for every 23 waters that you have in this crystal structure, 4 methanes are able to insert themselves into that structure. And this is found in sediment under shallow seas. And when it melts, the methane's released. Methane's a greenhouse gas. It causes warming, which causes more melting of these methane hydrates. Another one is from decomposition. So organic matter that has been frozen or is frozen tends not to decompose, but once you warm it up and it thaws out, the opportunity for that trapped organic matter to decompose and release itself in the form of carbon dioxide is there. Also, decomposition itself is an exothermic process which speeds up the melting of the permafrost even further. We have one more to talk about, which is desertification. And so with changing precipitation patterns, deserts expand. So we know that drier areas become drier, those drier areas become bigger, and deserts sequester far less carbon than forests or grasslands. So if you have a grassland that is conducting photosynthesis and building up soil structure and putting carbon into the ground, that can be a sink for carbon. However, if that grassland becomes a desert, you no longer have that sink, and so we are reducing the ability of the Earth to counteract the carbon that we are putting into the atmosphere. If we want to look at climate models, and we try to sum up all of these impacts, there's a lot of pieces that we have to look together. If we think about trying to quantify the impacts of feedbacks in polar regions, well, we have the ice example, but as it melts, the ice sheet becomes more unstable, which makes it more likely to fall apart. We've got the difference in albedo. However, when the ice itself melts, remember, melting is an endothermic process, and so that's a negative feedback loop. And so there's a whole bunch of different positive and negative feedback loops that work together. So while the ice is present, the melting ice acts as a negative feedback loop. However, the change in albedo is positive. When we get to class, we're going to talk about how all of these interact together. The role of feedback loops in the climate system is huge. Right? So far, we've kind of looked at everything in a really simple version, but all these interactions are pretty complicated. And if you would like to learn more about those, I've put some links in here that you can click on. Let's follow energy through the atmosphere, which we've done a couple of times. And in class, we've been concerned pretty much exclusively about greenhouse gases. But there are other substances in the atmosphere that play a role in the climate as well. And because of that, we must talk about aerosols. Because it's not greenhouse gases alone, it's things that absorb and things that reflect. And so while we were talking about albedo in the reflection category, I want to add in not just the surface of the Earth to that discussion, but I want to add in little small particles that are suspended in the air. We call these little small particles that are suspended in the air aerosols. And aerosols impact the radiative budget because they can absorb energy and they can reflect it. And different aerosols actually interact in different ways. They also influence cloud formation and growth. You probably learned in your earth science in middle school that clouds do not just form in perfectly clean air, right? There's dust, or there's some substances or nucleation sites on which that water condenses in the atmosphere. If we add aerosols, for the most part, to the atmosphere, for example, we have a volcanic eruption. It puts up a lot of particles up into the stratosphere. Well, that increases the planetary albedo. And so more light reflects off, the insolation we receive decreases, and we get a cooling effect. And so there's one example of how an aerosol acts is a global cooling effect. What particles do we have in the atmosphere that are aerosols? Well, we can have suspended water droplets in the form of clouds. You can have sulfuric acid or nitric acid, smog. There's tons of other ones. You can have dust, soot, black carbon, salt, and salt spray. And depending on what they are, they'll either reflect or absorb. And if we want to take a look at some of these sources of aerosols, one is vehicles, and diesel vehicles being particularly bad in the aerosol emissions department. And we can just see the difference. If we look at Beijing before a car ban was put in place for a military parade and after. Now, this air is much easier to breathe and isn't going to cause you as many respiratory problems long term as this air. But this air actually tends to have a cooling effect. And so when we clean up the air to make it easier to breathe, we actually reduce the masking effect that these aerosol particles had on the global warming. So when we clean this up, this gets warmer. Where do aerosols come from? Well, aerosols can come from windblown dust, they can come from volcanoes, they can come from soot and smoke from burning fossil fuels, they can come from clouds, sea salt from spray. From spray, bubbles, burst on the surface of the ocean. When they do that, they flick up a little bit of water, which has some salt in it. And those aerosol particles actually return to Earth. They are not generally long-lived in the atmosphere. They return to Earth when it rains. So that if you ever have spent time in a really a place with a lot of pollution, air pollution, you'll notice that the air tends to be cleaner after it rains because those particles get knocked out with that water coming down. We've got a series of sources of aerosols. We've got those from industrial pollution, primarily from North America, Europe, and Eastern Asia. And these tend to be things that are water soluble, inorganic. So being water soluble means they will fall back out when it rains. So organic carbon, elemental carbon, sulfates, nitrates, ammonium. We also get it from burning of biomass. So this is forest fires. You got wind-blown dust, and so we'll often see like sand and dust blowing across the ocean from the Sahara. That was talked a lot about in the summer of 2020. And then there's other natural sources of aerosols as well, coming from the ocean and landforms and existing just free in the troposphere. So here's an example of dust in the Mediterranean. Here's a natural source of aerosols. You've got a lot of desert areas in the Sahara, in northern Africa, and in the Middle East. And when wind blows, it can blow the dust, the really small particles in that desert sand, and go out across the Mediterranean. It can actually all the way across the Atlantic. We have forest fires in the United States West. In the year 2020, that was a really big story going on. We had California, Oregon fires going, and that smoke does have an impact short term on temperature. I do want to give you just like a couple of examples of aerosols that have been produced in cities that are kind of historically or socially important. And so, for example, coal emits sulfur and smoke particulates. It goes up into the air. And this was a big problem in London. And in 1952, it led to thousands of casualties because there was a cold inversion event. And what that means is, unlike normally, where we have in the troposphere the warm air near the ground and the cold air near the tropopause, and therefore we get mixing, that would normally lead to the dispersion of these particles. However, if an event occurs where you end up getting cold air under warm air, the atmosphere stops mixing, and any pollution that's being put up in the air, any of these particles and these aerosols tend to build up. They don't disperse. And at this point in time, Londoners were burning a large amount of coal for heating, and so the amount of particles in the atmosphere grew and grew and grew, and that causes respiratory problems and led to thousands of deaths. This was a good example of an impact that air pollutants played in human health, and this led to, at least in part, to passage of Clean Air Acts in the US and Western Europe. Before we move on to talk about the other one, I do want to point out that some potential cause of an inversion layer, because it doesn't make sense. How could the surface be colder? Right, the surface is what absorbs heat. Well, we tend to see places that have ocean upwelling have these events occur. So let's look at California. Well, in the coast of California, you've got ocean currents that are causing an upwelling of cold water coming up from the depths up near the surface. And no matter how much energy is striking the ground from space, that water is always going to be cold because we got new cold water coming up, and that cold water can cool the air around it. And so you can have events where despite the fact that you have energy coming in from space and being absorbed by the surface, that surface still being cooler than the air above it. This Great London Smog of 1952 is not the only example that has led to casualties. The Asian brown cloud is an annual event that occurs in South Asia every year between January and March. And this happens because the aerosol particles get trapped, they don't disperse, and this has been linked to about 2 million deaths per year. So, apart from their impacts on human health, how do these impact the climate? Well, most aerosols actually have a cooling effect. They're light in color, they reflect solar radiation, the world gets cooler. Some of them, however, though, such as black carbon particulates, absorb solar radiation and cause warming. So we can't lump all aerosols into the same category. We have to think of the cooling aerosols and the warming aerosols. So we've talked about how we can get these aerosols from combustion of coal and running like diesel engines, but there's also natural aerosol production from volcanoes. And I just want to share with you a couple of things that I've taken from Alan Robock from Rutgers University's lecture about volcanoes and climate change. And he's a professor in the Department of Environmental Sciences. And this is a really good resource to go to. So volcanoes play a role in weather and climate, both short scale and medium scale effects. And so if you have a volcano that's placed right, it can cause, for example, a reduction in the trade winds, which might cause an El Nino to be induced because you're no longer pushing that water west across the Pacific as much. And so that could happen start within a couple of weeks, but once you get an El Nino going or stop it from going, that cycle could be a couple of years. You can get a reduction in the daily cycles of warm and cold, and that happens kind of immediately, and that's really short term. Because of those particles going up into the stratosphere and being reflected mostly in nature, you get a summer cooling effect that lasts for a couple of years. Because we're blocking that incoming energy, we have reduced evaporation, so we get a reduction in tropical precipitation. And we also get a reduction in precipitation in Sahel regions. So these are some of our impacts of large tropical volcanoes. They can also cause ozone depletion, enhanced UV, which lasts for a couple of years. And overall, they have a global cooling effect near the surface. But they have a stratospheric warming effect because with all those particles up there, some of that sunlight that isn't able to reach the surface of the Earth does get absorbed in the stratosphere. And so you see the stratosphere get a little bit warmer as a result, while the surface in the troposphere gets cooler. And we also get slight warming of winters in northern hemisphere continents. Now, that happens in the tropics. If we look at volcanoes in higher latitude locations, so these would be things like Mount St. Helens, you get a cooling of the continents, and we get a reduction in both Indian and African monsoons. And when we get that, you can get a reduction in water flow in rivers that are fed by monsoon rains, which can impact people near their mouths. To sum up, volcanic eruptions, because of the aerosols they contain, cause short-term, like 1 to 2 year time frame, global cooling. We're going to continue with our summaries. Aerosols can directly impact the radiative budget through both reflection and absorption. They can impact the radiative budget through their effects on clouds, both reflection and absorption. And there are many different types of aerosols, and their composition matters as to what their effect is. They come from many different places, and these are often episodic sources. So while getting sea spray might not be episodic, getting a volcanic eruption might be. And these are generally short-lived in the atmosphere. They fall out with rain. And so their impacts are much shorter than those of greenhouse gases. You can remove the aerosols in the air around a city in anticipation of a parade by stopping the diesel vehicles. And these are often at the core of discussions of geoengineering. So you think about cloud seeding, for instance. Those are based off of aerosols. Aerosols reflect and absorb. There are man-made and natural sources. They're regional. You can have some cities that are dirty, some cities that are clean. They're short-lived. They tend to mask warming. So they reduce the impact of warming. And so if you remove those, the warming actually tends to show up. They change clouds, both precipitation and their ability to reflect and absorb. Volcanoes are natural drivers of climate variability due to their aerosols. And considering all sources of radiative forces that we talked about last time, greenhouse gases tend to warm, aerosols can warm or cool depending on their identity, and cloud-based aerosol effects tend to be overall cooling. I do want you to spend the rest of your time working on your models, and so we're going to cut ourselves off right about now. For your next class, you need to get yourself ready for our discussion of the Keeling paper. You need to keep working on your climate models, get your lab reports in. I hope you learned a lot today about feedback loops and aerosols, and I look forward to seeing you together in class next time. Bye-bye, everyone.